Hi, my name is Toby, and today we're going to learn about extraneous solutions of square root equations. You've already been introduced to solving square root equations, but we're going to take a little bit of a closer look into why exactly they cause potential extraneous solutions. By the end of this lesson, you'll be able to identify an operation that might lead to an extraneous solution, and you'll be able to identify equations where you'll need to check for extraneous solutions. All right, so the first thing we're going to do is give ourselves a little bit of a refresher on solving equations with square roots in them. So first thing I'm going to do here is just rewrite this problem. So we have a square root of negative 5x plus 16 is equal to x minus 2. The first thing we want to do when we solve this kind of problem is square both sides to get rid of the square root. So we're going to square both sides, and this will cancel with the square root, and we'll just be left with negative 5x plus 16. And on the other side, we're going to have to multiply out x minus 2 times x minus 2. That's not a problem. We know how to do that. So we're going to have negative 5x plus 16 is equal to x squared. And then we have negative 4x plus 4. All right. So the next step here is to get both sides equal to 0. And in order to do that, we're going to subtract a 5x or actually add a 5x and subtract a 16 from both sides. So plus 5x and minus 16 here. And of course, we have to do the same thing on both sides. So I'm going to add these down here to the like terms, and we can go ahead and write this out. Here, we're just left with the 0 as we wanted, and this is going to be x squared is plus 1, 1x minus 12. All right, so x squared plus x minus 12. The last step here is to factor. And what we're looking for when we're factoring is two numbers that add up to 1 and multiply out to negative 12. And that's going to be plus 4 and minus 3. So 4 times 3, or 4 times negative 3 is negative 12. And 4 plus negative 3 is 1. So we have our solutions here. Basically, to set this equal to 0, x has to be negative 4, and to set this one equal to 0, x would have to be equal to 3. So we're left with two solutions, x equals negative 4 and x equals 3. We're not done yet. We have to check if these are actual solutions or if they're extraneous. And the first one we're going to check here is the 3. So we're going to go ahead and plug that back into our original equation. Now it's always important that we plug it into the very original equation. So we have minus 5 times 3 plus 16. On the other side, we just have a 3 minus 2. Here, this is negative 15 plus 16, which is just 1. So we're going to be left with a root 1 is equal to 1. And this is correct because root 1 is just 1. And this is indeed true. So we are happy with this solution. Now, plugging in the other number, which was negative 4, or the other solution, we're going to do the same thing again here. So negative 5 times negative 4 plus 16 is equal to negative 4 minus 2. And we're left with a, so here we're going to have a 20 and plus 16, and this is just negative 6. So we can write that out as 36, so root 36 is equal to negative 6. And this is not true, so we are not happy with this negative 4. This is an extraneous solution. So an extraneous solution is a solution to an equation that comes through the process of solving that equation, but is not a valid solution. All right, so at which step did our extraneous solution appear? Well, let's just go through the steps and plug in negative 4. So if you remember from the previous screen, we came up with negative 4 as our extraneous solution. When we plugged negative 4 into here, we were left with root 36 is equal to negative 6, and this is not true. So we know this doesn't work for original equation. But at which point did this extraneous solution start working? So let's just go through the steps again. So if you remember, I'm just going to write this down over here, negative 5x plus 16, x minus 2. And the first thing we did is we took the square of both sides. So we squared both sides. And this gave us negative 5x plus 16 is equal to x squared minus 4x plus 4. And here we can already see if we plug in our negative 4, we'll go ahead and do that. So we have negative 5 times negative 4 plus 16 is equal to negative 4 squared minus 4 times negative 4 plus 4. Let's work this out and see what we get. We have a 20 plus 16, so that's 36, is equal to negative 4 squared is 16, minus 4 times negative 4 is plus 16, and plus another 4. So here we have, again, 36. So what you'll notice is this negative 4 started working after we squared both sides. This brings us to our next definition. That's the definition of a non-reversible operation. This is an operation that you can do in one direction, but the reverse is not always true. So squaring, which we saw in the previous step, is an example of a non-reversible operation. All right, so let's have a look at why squaring is a non-reversible operation. So again, by non-reversible, we mean it's an operation we can perform in one direction, so we can square something, but then we can't necessarily go back, or we can't know where we came from. So what do I mean by this? Well, if we're given two numbers, a and b, and we set them equal to each other, so if we know that a is equal to b, we can always square these and know that the squares will still be equal. So if these two are the same number, a squared will still be equal to b squared. This will always be true. But the reverse is not always true. So if we start with a squared is equal to b squared, we cannot always say that a and b are equal. So if we start in that direction, or we start with a squared and b squared being equal, we cannot say this. Can you think of an example that makes this not true? So let's try the numbers 3 and negative 3. So if we plug those in, so we negative 3 over here, and we square that, and we say that's equal to 3 squared, we can see that these are the same. So negative 3 times negative 3, the negatives will cancel, and we'll end up with 9. 3 times 3 is also 9. So we do have that a squared and b squared are equal. However, a and b are two different numbers. So a is not equal to b. So this is why squaring is a non-reversible operation. We can square a and b and know that they're still equal, but we can't go back. So if we start with a number 9, in other words, if we start with a number 9 here, we don't know where we came from, right? We could have been either a negative 3 or a positive 3. So if we want to start with 9 and take the square root and to reverse the operation of squaring, we cannot say where we came from. It's not reversible. We lose the information about the sign. So if we take a look at our previous example that we worked through, so we had the following equation. We had that negative 5x, so the square root of negative 5x plus 16 was equal to x minus 2. And in order to solve this, we had to get rid of this square root. So what we did is we took the square, or we squared both sides, I should say. And what you'll notice here, so after we square, we get negative 5x plus 16. What you'll notice here is we actually could have had a negative in front, and we would have ended with the same number. So if we squared negative square root of negative 5x plus 16, we also would end up with negative 5x plus 16, because a negative times a negative is a positive again. So in other words, after we squared it and continued to solve for x, we were actually solving for two equations. So first we were solving for the original equation, so that's this positive version, but we were also simultaneously solving, so after we squared, we were simultaneously solving for the negative version of this, so with a negative root 5x plus 16 equal to x minus 2. So you remember our answer, the extraneous solution that we ended up with was negative 4. So at the end we came to the two and we had negative 4 and we had 3. And we did check them and we noticed 3 does work. So when we plug this back in, it does work. But 4 does not work here. And that's because 4 is actually a solution to this equation. So if we plug in negative 4 here, we can check that this is true. We can plug in negative 4. So we have negative root of negative 5 times negative 4 plus 16 is equal to negative 4 minus 2. And we will solve this out. So we have a 20 plus 16, so negative root 36. And on the other side, we have a negative 6. Square root of 36 is 6, and we carry over this minus, and we have negative 6 equal to negative 6. This is a solution to this equation, so this works. And this is what happened. After we squared, we lost the information about the sign. And so we were actually solving for both of these equations, even though this was our original equation. This is really the only one we care about. This is what we started with, so we want to solve for this. And so this is why after you square, you always have to check all your answers. So I want to make a quick note here that it's actually not only squaring that ends up being non-reversible. Any even power, raising a number to any even power. So if we have a to the 4th power equal to b to the 4th power, we also cannot say, so we can also not say in this case that a is equal to b. This is not always true, because again, if we pick a negative number for a and the same number but positive for b, so if we have negative 3 again, and for b we pick, and we're going to take this to the 4th power, and for b we pick 3, also take that to the 4th power. What you'll notice is this is saying negative 3 times negative 3 times negative 3 times negative 3. And these two negatives cancel, and these two negatives cancel, because every even pair of negatives will cancel here in this multiplication. And we'll end up with 3 times 3 times 3 times 3, which is equal to this one, which is also 3 times 3 times 3 times 3. If we work this out, we get 81 is equal to 81. And the same is really true for any even power. So if we take it to the 6th power or the 8th power, we're always going to lose this information about our sign. So what about raising to an odd power? Is that reversible? Well, yes, actually it is reversible because we don't lose this information about the sign. So just to give you a quick example, if we're given that a cubed is equal to b cubed, we can always reverse this and know that a is equal to b. And just to show this to you quickly, if you remember, before we chose the negative version, so we chose negative 3 for a and 3 for b, and after squaring them, we got the same number. We didn't know where we came from, whether it was positive or negative. The same is not true here, because if we cube 3 and negative 3, we will get a different number. We will get, so 3 cubed, or negative 3 cubed here, is not equal to 3 cubed. This is why odd powers are actually reversible. So you only need to worry about non-reversibility when you raise something to an even power. And the most common case is going to be squaring. So before we wrap up this lesson, I want to go through this example problem here. So for which of the following equations will you need to check for extraneous solutions due to squaring? So in any of these problems where we're going to have to square in order to solve for x, we will want to check for extraneous solutions. In this first problem, we do see a square root. However, we don't need to square at any point while solving for x because there's no variable in this square root expression. So here, we actually do not need to solve, or we do not need to check our solutions after we solve for x. In this next equation, you'll see that this one looks a lot like our example problem. And because you're going to have to square to get rid of this square root over this variable expression here, we will indeed be squaring, and we will have to check. For this next one, we have an x plus 7 cubed. And all the operations that we perform in order to solve for x here, so we're going to take the cube root, they are all reversible. So we do not need to check here. On this last problem, we have to first convert this into a square root. Because if you remember, raising something to the 1/2 power is the same as taking the square root. So we can rewrite this as x equals the square root of negative 13x plus 27. And there's a plus 3, and after we subtract 3 from both sides, we're left with x minus 3 is equal to the square root of negative 13x plus 27. And here, in order to solve for x, we're definitely going to have to square to get rid of this square root. And so in this one, we will have to check. So what did we learn today? So we learned about an extraneous solution. An extraneous solution is an invalid solution that results through the process of solving an equation. We learned about non-reversible operations. It's an operation whose reverse is not always true. This is actually the thing that leads to extraneous solution in the first place. We learned that raising to an even power, any even power, is non-reversible. And also, it's important to check for extraneous solutions in these cases when we have a variable under a square root in the equation.